the basics here. Also, as we begin, this is the start of Unit 1. There will be some jargon and some vocabulary associated with this unit. In fact, I would argue that this unit is mostly vocabulary. I can't really say that what we are going to be doing is a physics unit, because it really isn't. It's the language of physics, but it's not really physics. There'll be no explanation of why things happen the way they do. We're just finding ways to describe what is happening. I want to be, yes? You may go wherever you wish. I don't stand on principle for seating charts. So I want to be kind of clear from the get-go that as we go through this worksheet, I'm using this as a conduit to deliver information about vocabulary at the same time as we do some kind of mathematical comparisons. As I introduce new topics, I will attempt to let you know when I think these are the important foundational pieces of material that you should be writing down. But I want to be very clear, this is the start of Unit 1. And the vocabulary of this unit is critical. You already have a large vocabulary of words that share the same words that I'm going to say, but my definition and your definition probably don't agree. But you have to use my definition for these words, especially when it comes to test taking. Several of these words are going to sound the same, but don't have the same meaning. That's just as important, that you understand that they may sound like they're all the same words, or you think they're all the same, but the minutia, the important details, is what's going to be tested. And I can't say that the AP exam won't attempt to trick you. I think it will. I think it will purposely choose one word over another, knowing that there's a subtle difference in the two words in anticipation of trying to see if they can trick you. Does that make sense? Some of the words I'm going to use today also aren't vocabulary words, but they are related to our vocabulary words, and you'll need to know them as well. So let's start at the very beginning here. This says it's a velocity worksheet, and it tells me right from the beginning that I am comparing position versus time. I'm going to present you with graphs a lot in here. A lot of what we communicate to each other is on graphs, but a lot of the graphs you guys have used in your other classes are going to be different than what we do. Our graphs are always comparing two sets of data. This one is comparing position data and time data, and that's clear from the description and it's clear from the graph, right? And they're using symbology here that you have to be prepared to use as well. They're telling me that they're going to use the symbol X to represent position, and that it's in meters, and they're going to use the symbol T to represent time, and it's in seconds. Right? That's the information they are giving us from the start. So, without further ado, can the folks at Gotham answer the first question? Do the cyclists start at the same point? How do you know? If not, which one is ahead?
You said that the cyclists do not start at the same point, and by looking at the graph, you can tell that B is clearly higher than A.
All right. So they had a lot to say there that I think is great. This portion of our graph, what do we call it? This is the origin. Our graphs, especially dealing with time, should always start at 0. All right, that's our attempt. It's implied. Now, we don't know if that's actually true here, but it's implied. It's definitely implied when dealing with the time. You have a name for this point. What do we call it? The y-intercept. Except we're probably not going to use the y-intercept as much. We'll probably use the vertical intercept. Is that okay? So, because this is the position at time 0. Right? That's what's being indicated here. And the group said that B was at a different position than A at time 0. Does anybody have the word higher written on any question here when dealing with the comparison between A and B? Okay. Now, just you two? So none of your other answers? Okay. I think it's very common to say higher. I want you to strike that from our work here. We tend to think of the top of our page is up, even though it's pointing north, truthfully. But we tend to think of the top of our page as up. And we would say something is higher up on the graph. But that's not what's being depicted here. One cycle is not above the other. You follow me? This is a number line, and it's in the horizontal direction, or at least it's suggested that it is. These are cyclists. They're on the ground. They are biking. So my expectation is that one isn't higher than the other. One is further away from the origin than the other. That's the terminology you should use. further away from the origin. For us, we know about motion detectors. We would say it's further away from the detector if we were using a motion detector to track motion. But don't say higher than. That implies something that's not being stated. We are only going to be dealing with one-dimensional motion for the time being. So our motion could be up and down, left and right, forwards and backwards. That's fine. It's all one-dimensional motion. But try and put it in the context of a question. Here, I think we would say cyclist B is further away from the origin than cyclist A. That's how I would like you to phrase it. All right, at t equals 7 seconds, which cyclist is ahead and how do you know? Hoth?
We said that line A would be ahead because it's positioned further.
Okay. I think there's lots that's okay with what they just said there. A little stumbly, but all right. Do we know where 7 seconds is? We just know it's over here somewhere, right? So we don't really know where it is, but does that really matter? Can we all agree that cyclist A is further away from the origin for this entire region than cyclist B?
Yes.
All right, good. So we don't have to know exactly where it is. All right, so it says which cyclist is traveling faster at t equals 0? Let's go with, I don't know, how about Paradise Falls?
Are you talking about C at 3 seconds here?
I'm talking about question C.
Yeah, okay. Cyclist A, after 3 seconds, the line in the time graph is steeper gaining distance on B.
All right. You use the word steeper. Does line A's graph always steeper than B?
Yes.
How many of you agree that the line for A is always steeper than the line for B? What word do we use to describe the steepness of a line graph? All right, so let's have a bit of a side discussion here about slope and area. Whenever we are asked to evaluate a graph, you should evaluate it for a number of principles. For us, since our graphs are always going to be comparisons of data, you should always first understand what is plotted in your graph. This is a graph of two objects telling us the relationship between their position and time. Right? That's what this is a graph of, and that's what's communicating to us. Everybody follow that so far? But for every graph, you should go further. I'm going to be putting a lot of graphs in front of you, a lot over the course of the year, but there's always the possibility that AP Central could present you with a graph that I have not been able to present to you myself. So there are things I need you to do when presented with the graph that go beyond just what's on the horizontal axis and what's on the vertical axis and what trends do you see. One of the things you will have to do is evaluate them for slope and area. To do so is not hard. For slope, what I'd like you to do is take the units of the vertical axis and put them over the units of the horizontal axis. So our vertical axis is meters, and our horizontal axis is seconds. And then say the unit using the word per for the line. Our unit here is meters per second. Does meters per second conjure anything in your mind? Does it sound like something that you might know about? All right, so somebody just said speed. I think it probably does. Miles per hour is one that you know too, right? Miles per hour, meters per second are similar. Now, I don't want to be a little bit, I don't want to be sneaky here or anything. You may not recognize the units of a slope. That doesn't mean they don't have meaning. It just means they don't have meaning to you because you don't recognize them, right? Not every slope and area will mean something. Our job is to figure out if it has meaning for the things you already know about. And right now, meters per second, it's not unreasonable to think that this could be speed. On the other hand, area, you take the vertical unit, meters, and you multiply by the horizontal unit, seconds. And I get meter seconds. There's no per in there, you just say them, meter seconds. Do any of you have anything that sounds like? Any unit of measure that you've heard about that's in meter second? All right, so it may have meaning, but it has no meaning to you. You follow what I'm saying? All right. Now I will want you to do this for every graph with which you are presented. However, I will also tell you about specific graphs. This is a position versus time graph. The area has no meaning, and the slope is about speed. We got it? That's always going to be true. However, let's just skip back to this for just a minute. Here's where we need to have a longer aside. There is the term speed and the term velocity. They are not the same. Speed is a scalar quantity, and velocity is a vector quantity. Vector, you know, the guy from Despicable Me when you were kids, the little creepy guy. But his catchphrase is for real in this class. He commits crime with both magnitude and direction. Vector quantities have both magnitude and direction. Scalar quantities only have a magnitude. So speed is how fast you're going, but velocity is how fast you're going and in what direction. So when we talk about the slope of this graph, do you think it tells us the speed or it tells us the velocity? I believe it tells us the velocity. I believe it tells us what direction the object's going, because that's a great question. And so let's look at this graph for just a minute. You are the one who said in class just a few moments ago that the slope told us the speed. Excellent. So which of these two is traveling faster?
A,
How do you know?
because the slope is at further away from the origin.
Well, I wouldn't say that the slope is further away from the origin. I'd say the slope is steeper.
Mm-hmm.
Is that okay?
Yes.
All right. They're both traveling in the same direction, so they both have a positive slope. So they both have the same direction to their answer, but A is faster than B. We are comparing the magnitude of their velocity. The magnitude is the size part. In fact, the word magnitude means size. Whenever I say the word magnitude, I can replace it with the word size, and the sentence would mean the same thing. Is that okay? Mm-hmm. So speed is the magnitude of velocity. So a velocity graph is a speed graph because it does tell you the speed. It's just that the position graph also tells you the direction. So because it also tells you the direction, we would say that the slope is velocity, not just speed. Is that okay?
Yes.
All right. Excellent. So I want to cut to the chase here. Is there ever a time when A and B have the same speed? Do they ever have the same slope? At 5 seconds, what's happening?
They're intersecting. They're passing paths.
They're the same distance.
So they're at the same position, right? They haven't traveled the same distance. Which one traveled further?
I just they're the same distance away from this point.
They're the same distance away from the origin. That is definitely true. So we could probably say that A is passing B at that mark, right? That's what's happening. But at that instant, they're at the same place for that moment in time. But after that, A is always ahead. And before that, B is always ahead. So A is passing B at that moment. Good for you guys? All right. There are modifiers to these words that don't always mean the same, that change the meaning. I don't want to spend a lot of time on it right now, but I will come back to it. The first is instantaneous. Instantaneous. The other one is average. So there's instantaneous speed, instantaneous velocity, average speed, average velocity. If I ask for something's velocity, I'm usually asking for its instantaneous velocity. But instantaneous technically means velocity at an instant in time. So this refers to a specific instance or moment in time. So what is the instantaneous velocity at 7 seconds? Something like that. Unfortunately, average speed means something different than average velocity. When I put average in front, I am creating a technical definition, meaning this means something specific that's not about velocity or about speed. Average speed is an equation. It's total distance traveled over the total time interval. Where average velocity has a different definition. It's total displacement over the time interval. Got to be a little careful about these because these are technical definitions. They're not averages in the sense that you're used to them being an average. Now, how many of you traveled to school today from home? A lot of you? All right. How many of you are likely to head back home by the end of the day today? Displacement means change in position. That's what it means. So the vast majority of you will have a total displacement today of 0 because you will return to where you started. Does that make sense? That's what displacement means, change in position. Now, distance is how far you've gone. So if the school is 10 miles from your house, you'll probably travel 20 miles today. 10 to get here and 10 to get back, not including what you did when you were walking around campus today. I'm saying this because distance covered is different than displacement. You'll have a displacement of 0 over the course of the day, but you will have traveled clearly over 20 miles over the course of the day. So when we talk about distance and displacement, we are talking about different measures. Displacement is a vector quantity. Distance is not. Displacement is a vector quantity, but distance is not. All right. Over to this one for just a minute. How is the motion of cyclist B in this graph different than the motion of cyclist A in this graph? Go ahead.
They're going in opposite directions.
How many of you would agree that they're going in opposite directions? It looks to me like cyclist A is traveling away from the origin. And it looks to me like cyclist B is traveling towards the origin. So they do appear to have opposite directions. Moreover, what would you tell me about the slope of A versus the slope of B? Stuff you've learned in your math class. Yes?
The slope of A is positive and the slope of B is negative.
How many of you agree with that statement? Okay, positive and negative slopes. Let me go back to say here that one was traveling towards the origin and one was traveling away from the origin. I know that you think direction is more complicated than that, but for the first couple of weeks, we're only going to deal with one-dimensional motion. So for us, one-dimensional motion means forwards or backwards, up or down, left or right. Never both at the same time, not up and to the right. All right, that'd be two-dimensional motion. Yes?
I have a question on like, how would I be able to tell the difference between speed and velocity on a graph? Like, how would I tell like, oh, that's a speed graph, or like that's.
I'm going to assume that this page is largely the same as the other page, but this one, maybe we have more questions about? Second and third certainly did. So let's start by talking about the position versus time graph that we have there. Did anybody have difficulty finding the velocity from this graph? It's a straight line, isn't it? So did you find the slope? So I did the slope by doing rise over run. it rose 50 meters in a time of 6 seconds. So I found that the slope was 56 meters per second, or 25 thirds meters per second. Or if you used your calculator, maybe 8.3 meters per second. That all good? How do we do on the mathematical model? We need help with that? Anybody need help with the mathematical model? No? So I can just pick a table? I'm okay with that. All right. Let's see. Let's go with bikini bottom. Anybody at this table get it?
Units, but I think the model might be right.
Let me hear it.
I did y equals 10x plus 10, but I know those are wrong.
Okay. There's a problem with the model, but I can see where your model started. How many of you used y equals mx plus b as your model? Excellent. Now, there's no y's here. What is actually plotted on the vertical axis? X is, right? They're using the symbol X for position. So X is plotted on the vertical axis. We don't use the unit, we wouldn't put M here for meters. We would say X, because that's the symbol that's being used to denote position. That's pretty common. What's being plotted on the horizontal axis? Time. So I would use this lowercase t. That's not an accident. Lowercase t is a symbol I wish for you to use for time. Uppercase t has a different meaning. We have a lot of symbols. What does M represent? Slope. So 8.3, the slope of our line. What does B represent? So 10, right? That's our y-intercept. This is the model. So our models will not always be linear. They will be quadratic. They will be linear. They will be other things. You're supposed to be able to read information off a graph and be able to determine what it's talking about. We good? Got 5 more minutes left, so I really would like to talk about this graph for a minute. What is being plotted here? Velocity and time. So this is a different kind of graph, isn't it? Yes. So did you test it for the meaning of the slope and the meaning of the area? Now that we know to do that, let's do it real quick. Because you probably didn't do that, but we know to do it now. Slope would be to put whatever's on the vertical axis for units divided by what's on the horizontal axis. Vertical axis are meters per second. Horizontal axis are seconds, so this is meters per second squared. Does anybody know this unit? So I'm going to assume no. You don't have to know it. If you don't know what it is, then it just doesn't have any meaning to you. It does have meaning. This is the unit of acceleration, which we'll come to next week. But you didn't know that, so it would have no meaning to you. Area in this case is meters per second times seconds. What would that work out to be? Meters. Is there anything that you have measured in meters before? What? What do you measure in meters? Distance, sure. Could distance be a measure in meters? It's plausible that the area of our graphs here measure a distance. Now, you guys are sharp. The object's traveling 4 meters every second. How far did it go in the first second?
4 meters.
How far did it go in the next second? Another 4. So how far has it gone?
8 meters.
8. That's not a surprise, right? Now, we're saying that the area under the graph should tell us 8. Now, I'm going to assume that you guys don't know how to find the area under a graph, but I'm going to tell you that the area under graph is the area bound by the curve and the 0 axis. If you didn't know that, write that down. The area of a graph is the area bound by the curve and the 0 axis. For us, that's this. The area bound by the curve and the 0 axis. This is a rectangle that has a length of 2 and a height of 4 meters per second. The area of that, 2 times 4, right? 8 meters. Looks like I have an area here too, don't I? And don't be concerned, this is a height of -3 meters per second. It is negative. You can have negative area. It just indicates direction. And this, 1 second. -3 times 1 would be the area of this section, and that is -3 meters. There is no area here, right? There's no area between the curve and the 0 axis. It's on the 0 axis. This suggests to me that my object went forwards 8 meters, backwards 3 meters, and then stopped. What distance did it travel? 11 meters. Forwards 8, backwards 3, that's 11. How far away is it from where it started? Guys, you got this one? Walked forward 8, backwards 3. How far away from where it started?
5 meters.
Displacement of 5, distance of 11. All right. I suspect you could do this graph now
Yep.
because it went forwards,
Yeah.
backwards, stayed in place. All righty.